Welcome back, ladies and gentlemen, to our fourth section in applications of trigonometry. This is vectors on a plane. Now, in this section, we're going to cover a lot of the definitions of a vector that we'll kind of further explore with some examples in the note section. But I want to kind of introduce to you what a vector is if you're not familiar, as well as some of the ways that we are going to represent vectors and what we can identify from them. So the first thing is, if we have two coordinate points, right? And you could plot those points, and it's important to understand from those points, we can find the vertical, the horizontal distance. We can also find the distance between those two coordinate points. Now, what's interesting though, between two coordinate points, like when we're finding the length, we don't really consider the length and the direction, right? It's just kind of like 5 or D. We don't really consider like from B to A or from A to B. And that's the way that a vector differentiates from just the distance between any 2 points, because what a vector is what we call a directed line segment. You basically have your initial point and your terminal point. So it's saying you're going to start at your initial, and then it's going to show direction towards your terminal point, or the final point in the case. Now, when we are going to just introduce some new notation, hopefully you recognize here to be the distance formula, right? So we recommend the final point or the terminal point to be x2, y2, and the initial point x1, y1. So you can see we're just finding the horizontal and the vertical change, those distances, squaring them, and then taking the square root to find what we call the magnitude between our 2 points P and Q. Now, the distance is not going to change if it's from P to Q or Q to P, but it's just kind of this formal process. See, if we need to find the magnitude of a vector, we're basically going to be finding the distance between those 2 points. Then we're going to look at the component form. And what component form does is that just kind of simplifies our vector. So rather than, always writing out these, 2 coordinate points, the change or the difference between them, we can represent them as, the horizontal change and the vertical change, or those differences horizontally and vertically. And we represent those as like V1, V2. And you could also see that also for a vector where you have these slanted parentheses. So rather than finding the difference between these two values, we can just represent V1, V2 to represent our vector V. It's also nice when we have it in component form, since we're not dealing with initial and a terminal point, we can name our vectors like V or W or U, giving them a name because they are just in more of a simplified form. It also helps us when finding the magnitude, whereas you can see this a little bit more resembles the Pythagorean theorem, right? Because V1 represents the horizontal change, V2 represents the vertical change between your initial and your terminal point, and then obviously you have the magnitude V, which is going to represent the magnitude or the distance between your initial and terminal point. But here we're looking at it in our component form. Now, just like with any, kind of triangle or looking at the points, we can also find the angle of the vector. And to find the angle is basically going to kind of look at, if you have that picture of the vector, you can see V2 would be the opposite side, V1 would be the adjacent side. And so the angle of the vector is going to be represented as theta. And we could find that angle using the tangent of theta. So it's just very helpful to have that component form. This is going to simplify the formula for us to be able to identify the angle. Now, the nice thing about vectors is we can also do some operations with vectors. We can add vectors together, as well as we can scale vectors. That means going to compress them as well as stretch them. Now, what we're going to do is we're going to work on applying these operations algebraically. We're also going to work on graphing the operations so we can visually see what is happening when we add, subtract, as well as apply a scalar to a vector. And one of the name of when we're like adding or subtracting is what we call the tail to head method. And that's just going to be a technique that we're going to apply to go ahead and help us graph the operations for our vectors. Then we're going to kind of take a look at the unit vector. And the easiest way to understand the unit vector is it's basically going to have a magnitude of 1. So, vectors can point in any direction, right? They can have kind of any angle. But what we can do is if we apply a special scalar, which is 1 divided by the magnitude of the vector, we can have that vector have a magnitude of 1. And that's going to help us kind of be like, the unit is kind of like your basics, your basis of your vectors. And we're going to apply our unit vector to understand the operations operations, as well as the characteristics of our vectors. Just again, kind of like what component form did for us from standard form, like it just simplifies the vector. That's what the unit vector does for us as well. Because we can look at the unit vector as any vector with a magnitude of 1, but we can also look at it in terms of standard unit vectors, which these are going to be unit vectors in our vertical and horizontal distance, basically unit vectors going up the x as well as the y axis. And we give these we describe these using I and j, which is another way that we are going to be able to write our vectors. Rather than using component form, a lot of times we'll write vectors in terms of their standard unit vectors, I and j. And the important thing when we're representing these I and j, you can see this is what we call our linear combination. So it's basically taking a component form, v1, v2, and you're just multiplying those values times your unit vectors, I and j. And so you'll kind of see, we'll use these forms interchangeably throughout the kind of process problems that we're going to be dealing with. But it's just important to kind of understand your I and your j, and then how we're going to use how they're going to relate to a vector in component form. And then we'll also look at the components of the vector. So it's important when understanding the unit vector as far as the cosine of angle, cosine of theta, sine of theta, which that represents another unit vector. Because if you think about that, based on whatever angle, that's going to give you, it's going to have a terminal point that's on the unit circle. And remember, the unit circle is going to have a radius of 1. So if we can take that unit vector, which is again a unit vector just like I and j, if we multiply that by our magnitude of our vector v, we can write any vector that we want to based on its angle as well as its magnitude. So there's a lot of different ways that we are going to use vectors to understand vectors, as well as apply different operations to be able to solve problems with our vectors. So this is a very important unit. There's a lot that we're going to cover and get a basis on for our understanding of vectors. And that's all going to start with getting in and reviewing all of the notes that you have in this section. And once you kind of feel comfortable understanding, all the different formulas you have, then we'll go ahead and get started working on some practice problems in the process videos where you can actually work through some of these steps and getting familiar with understanding vectors a little bit closely. And then once you're done with the process video, it is time to go ahead and check your understanding with the Check Your Understanding quiz. So I look forward to seeing you in the next video. I'll see you then. Cheers.